Hello and welcome back to Physics for the 21st Century. Again, my name is Greg Perugini, and the topic for today is moment of inertia. What do we mean by moment of inertia? Well, if we think and remember back to the equations where we were talking about force, and of course one of the fundamental units that we deal with is mass. If we're rotating something, we have to think not in terms of just force, but we have to think in terms of the torque that is involved over a radius. And we'll get into this more in the next chapter. But if I'm pivoting something, a force down will cause a rotation, and the torque being force times that radius, or the distance from that pivot. So that's well enough, but if I'm rotating something, I can't think just in terms of mass. Mass, in terms of just looking at it in terms of translational or linear, it has its equivalent rotational to moment of inertia. We have to take into account the geometry of that particular object. So if we look at that, and we will cover torque in a separate topic, as I said. Just a little bit of a review here. If you remember, when I rotate something, I think in terms of radians, and a distance in meters can be thought of as the radius times the radian, number of rads, if you will. And of course, we have an equivalent of velocity in terms of rads per second. So when we think along these lines, when I rotate something, I have to get in my mind that I'm not just talking about mass. The equivalent of mass rotationally is moment of inertia. And every shape and geometry has its own moment of inertia. For instance, if we look here on the screen here, if we have a long thin rod that is rotated through the center, its moment of inertia is 1/12 mr squared. Excuse me, 1/12 ml squared, pardon me, where L being this length. If I'm rotating it from the end, let's say this end, it is 1/3 ml squared. So we're going to be using moment of inertia in torque calculations later on, as well as angular momentum. But right now, let's just get down moment of inertia, and well, let's look at a problem. Why not? So let's say, I might even have a picture here. Hold on. If I'm rotating something, I'll just cover this topic right now. If I'm rotating something off center, let's say I am rotating here, not here, I can take the moment of inertia for that point that we know and take mass times this distance squared and add that to get a new moment of inertia. And this is called the parallel axis theorem. But again, I digress a bit there. So let's look at this example. We're going to have this rotating double baton here. And as I rotate this, if we model these as particles, I equal mr squared. So what's the moment of inertia of this? Let's assume these rods are weightless for the moment. So we're going to define little m as equal to 2 kilograms, let's say, and big M as equal to 4 kilograms. And these distances, let's say the distances are all equal, the radius being 0.5 meters. We're rotating off this center point. What is the moment of inertia here? Well, it is 2, the mass, times the radius, 0.5 squared. For the small ones, we have 2 of those, plus 4 times 0.5 squared for the larger ones, and we have 2 of those. So the moment of inertia of this system here is 3 kilogram meters squared. Okay, fairly straightforward. Let's look at something different here. What if we had a pivot in the center, like a propeller, with weights at both ends? So I have a pivot at the center, weights at both ends, and mass. Well, let's make it simple. I'm going to put just a mass at one end here. Okay? So we're going to say that the length of this is well, let's go with 5 meters. Okay? Now if you remember, let's go back to that one slide. If we pivot off the center, the moment of inertia for that rod is equal to 1/2 or 1/12, excuse me, ml squared. The ball we're going to model as a particle, mr squared. So if I have, let's just do it for one ball here to make it easier. One ball here, and that ball is 2 kilograms. So the moment of inertia of the rod pivoted on the center point is 1/12 times its mass. Let's say the rod is a 2 kilogram mass. times its length, 5 meters squared, that's going to give you something like 4.17 kilogram meters squared. The moment of inertia of the ball on the end is mr squared, which is 2 times the radius here, which is only 2.5 meters, right? We're off this point here is 2.5 meters. If the whole thing is 5 meters squared, that's going to give me 12.5. So, for this entire system here, with the ball at the end and the rod, the total is 16.7. So, moment of inertia can be added together for a rotational system like we have here. So again, if I have a rotation on an off axis where I don't have the geometry, I can use the parallel axis theorem. So in summary, have your geometries on hand. That guide point, let me go real far back here. Have this chart on hand when you take your assessment. Remember, where you pivot matters, because the radius, as in the example I showed, is 2.5 meters, but the length was 5 meters. Know your parallel axis theorem, and make sure you practice the problems in the book and online. And good luck to you. I hope everything works out.